Let's continue our lecture on the atom-light interaction. Last time we were able to formulate the equation. Well, first we make a kind of general view of the light-atom interaction. You know how the electromagnetic composition of the light interact with the charge, and even more than the charge, interact also with the spin of the electron. But in a first approach, we consider only the charge of the electron, and we were able to compose a kind of equation, which is the wave equation, but now having two parts. One part which is dealing with the original atom. So if you don't have any interaction, if you don't have the vector potential, means absence of light, then this gives us the solution of the conventional atomic system. We have from up to here, we have the electron bounded by the Coulomb potential. But the presence of the electromagnetic field in some frequency omega add this term, and this term represents the interaction. And it's this interaction that will cause all the changes. And we already saw that the change that happens is because this is time dependent. We have to keep the time dependence on the equation. And as a consequence, we're going to have the atomic orbitals, atomic or molecular, that happens for molecules too, will change from one to the other. And we discussed that, you know, the collection of states for this solution is everything that the system can be. So anything it can be has to be composition of those. And this will, in some sense, make the system goes from one to the other. Based on those discussions, we were able to propose that the solution for this time equation, remember the vector potential is now time dependent. We saw that the solution has to be a sum of functions. Of course, this psi is psi of r and t, and it is a sum of all possible solutions. So the presence of the radiation oscillating, and when oscillate means that this is on and off all the time, oscillates, is big amplitude, goes down, comes back. That's the oscillatory part of this vector potential, as we saw before. And what's going to happen is that we're going to have a superposition of the solutions of the state of the original system with the time dependent. You know, remember, if we just forget everything, the time dependence of each state is an oscillation with a frequency that's energy divided by h bar. And therefore, this is the full time independent and time dependent solution. But now we have a coefficients on this sum that's depending on time. So the electromagnetic field actually comes and change those coefficients in time. So there is a time equation for each of those coefficients, and that's is the main purpose of this determination. And of course, we have to remember that the psi k are the solution of the original atoms. So the light comes and changes the probability, because this coefficient square is the probability for the system to be in any of the psi k state. So it's like starting a state. We have to have a starting point. The radiation comes, will make the system to change to other possible states. And this is what we call the transition, the electronic transition, from one state to the other. And this is due thanks to the interaction that we have, thanks to this term here, which represents the interaction of the light with those orbitals. Okay, so we stopped here last time, and before I continue, I had to remember you of a few important things before we come and propose the solution or the equations, because now we have a function that's supposed to be the solution, and the only thing that we do not know are those coefficients. We have to determine those coefficients, right? And they are time independent, so we're going to take this. We know that when we plug this solution in this guy here, right, will be a sum of coefficients time, because this is solution of this. So we know that this will give us EK, which is the energy of the K level. The sub-index K represents the many orbitals, the many collection of quantum numbers that we can have. So it's easy, because when we plug this here, this part all together will give us the EK, which is the solution. Basically, you see this part here acting on this function give you E, the energy of the state. And then the time variation will produce a time variation of the coefficient. And here there is a sum. So actually this equation is a sum of many things. But then, before I continue, I want to tell you something very important. The collection of orbitals that are solution of the atomic system, they compose what we call a complete set, right? I said that before, and this is true for any quantum system. A complete set means a set of function that for that system is the whole universe. That's everything the system can be when isolated. But more than that, this complete set, right, they are like a collection of functions that allow us to express any function in terms of sum of those functions, composition of those functions. It's like when you have any function and you decompose in Fourier series, you basically decomposing in sines and cosines. And by the way, sines and cosines are solutions of the wave equation, demonstrating that sines and cosines are a good set, a good complete set, and they are orthogonal as well. What means to be orthogonal? Means that they are independent, linearly independent. You know, the closest similarity we can have is with the vectors. You know, we know that there is always a base. It doesn't matter what's the dimension of the space that we want to represent a vector. We always do expressing that vector as a sum of many components. And those components are in specific directions that are orthogonal directions and compose a little set of linear independent vectors, which is the basis, like the little x, little y, little z. Any vector in 3 dimensions can be expressed as a sum of those with coefficients that depend on the component in each direction. Here is equivalent. Here, and we know that the scalar product between, or the dot product between two independent, linear independent vectors is 0, because they are orthogonal. You cannot represent one with the other, right? They are fully orthogonal. That happens also with the functions that are solutions of the atomic system. They are a complete set, and as a complete set, they are not only orthogonal, but they are orthonormal, which means their norm, if I just integrate this, is either 1 or 0. So normally when we have 2 states, that's a way to represent this integral, okay? We call brackets. This is just a notation, the way we represent this product. And this is, actually, they are orthogonal, right? And when I make the product of 2 states that way, I get a delta function, which means this is not 0 only if K1 equal to K2, so the same state. And as I told you, which is the most important thing, any function can be expressed as a sum of this complete set. And that's important. Why? Because see, if you remember from mechanics, when we have a vectorial equation, what we do? We try to see what is the equation for each component. That's what we do. And normally you have a vector equation with time dependence and everything, and then we multiply by one of the components of the basis. And when we do that, we project and we say, how is the behavior of this equation along this basis, along this component, along this axis if it is a vector. We're going to do the same here. We start with a very nice equation. We start with this equation. We put this solution that will have sum everywhere. So I'm mixing all the functions. But then I come and I project, I make a dot product with one of the specific functions. And then I project this on that function, on that line or on that basis component, essentially. So when I have this and I have this as a base, this differential equation actually is a sum of many equations, because this is like a vectorial equation. When we have a vectorial equation, actually we have three equations in three-dimensional. We have one equation for the x component, one for y, one for z. Here is the same. Having this equation and this solution, we can come and look how is the behavior in each component. That's fascinating, right? Because due to this property of those functions, we can do all that. Therefore, we're going to start our problem, and that's an important point here. We're going to start saying that, imagine that when we turn on the light, or when we start to count the time, this is a time-dependent interaction, right? The system is in an initial state that we call psi A. So psi A is the original state. The atomic system is in some orbital, which is psi A. And what we're going to do now is turn on the radiation, or start to consider the radiation. And the radiation can take you to any other state. So even though I'm not going to do the full calculation, I'm going to show to you how you do it. You just come, take this solution, and let's plug in this equation. What's going to happen is that we're going to have a sum here of time variation of the CK. And here this term will be CK times E of k, because this term here on the function psi k is just ek psi k. And that term is the term that's a little different, because we have a many mathematical operation on the function. And that mathematical operation can make a mixture of those states. Can take one function that looks like 1k and looks more like a k prime. So one psi k can be more like a psi k prime. And that's the transition that we're going to observe. But basically we have a set of equations. We take that set of equations and we project in each of the bases. Projecting in each of the bases means multiplying scalarly by some function. So we say that our system starts in one state, and this will evolve now. So the system is originally in one state, and the interaction is on. Then the solution is given by that sum, and we're going to multiply that by project what's going to happen in any situation. Normally what we do, we say the following. We take the equation, we put the solution, and the solution means that the interaction can take the system to any possible solution of the original system. And then we multiply by psi A. So the system is in psi A, so what we do is we know psi A is solution, so we plug here, right? Psi A is actually in this sum. So we put there, we know the system is originally there. So in t equal to 0, all the coefficients zeros out except the CA, which is the state A. And then we plug in the equation and we multiply by a generic solution psi B. Psi B can be anything, any other state. So by multiplying, we are projecting all the system, everything the interaction can do in the direction B. So basically what we determine that way is the CB coefficient. And then there are many other steps we can do. And we end, after this calculation, which I'm not doing, but it's easy to find in many books. But by lack of time, I'm not doing detail. What I want to tell is that this solution, this equation with this solution and the properties of the function allow me to make a procedure to determine what is the time variation of each coefficient and what's the solution. But what we are really interested is the CB or any CB or any CK here. B is a generic state. We want to know all those coefficients because they represent the probability of the system to be in some other state. And if we do this procedure correctly, we find that CB for any instant of time square is given by this, depends on the amplitude of A, which is the intensity of light, depending on those constants, which is the electron charge, electron mass, and the speed of light. Depending on this integral. Here comes the interesting part, this integral. Because this integral, I told you that if I don't have anything here, if I don't have those terms, right, this is only non-zero if A equal to B. But because of the interaction now may change the initial state to some state B. Therefore, this integral may not be zero due to this action, due to the fact that the electromagnetic field, which is giving here, oh, by the way, here I already introduced the dependence of the A vector with space and with time. And I separate the integral in space, and then what I'm going to have there is a dCB dt. And then I integrate in time to get CB. And this is what I get, that because all the time variation, they are in the state through this term, and in the A to the term e to the exponential of I omega t, right? That's the A vector for the radiation. So this is not a hard thing, it's a very straightforward. Once we get who is dC B dt, that's how we're going to get to that equation. We make an integral and then I just square, because took the modulus and square. And what we have here, as I told you, is this term here, which is one integral that is not zero only if the radiation is able to modify the state A to project a little bit on the state B. That's one thing. And the other thing that we have to pay attention, is this term here, which is the time integration. Remember, because the states, they oscillate like E. Oh, let me use a blue color. The states oscillate like e to the minus I A E, that energy of the state, T divided by H bar. These things here we call omega. And because we're going to have two states involved, A and B, omega BA is basically the energy difference expressing frequency of the state A and B, between the state A and B. Omega is the radiation frequency. And epsilon here, because we had a vector to start with. Remember, when we deal with the interaction in the original equation, this is a vector. And this vector has a direction. And that's related to the polarization of the field that we call epsilon head here. So all those quantities are here now. But this element here, this integral, is very interesting because this one we know, right, is the integral of exponential. That is going to provide us a delta function. But this one, it's only going to be non-zero if my interaction, which is basically this is the origin of this term comes for the A there. If this term is able to act on the state A and modify it such that it looks like the state B, then this integral here will not be zero. So why I'm insisting on this? Because that's the essential part of the electronic transition. You know, the electromagnet comes, acts in one state, modify it to look like the other. And when that happens, the system may stay in the other or may return, as we're going to see. We normally call this a matrix element, and is non-zero only when this action on the initial state, because remember, we start now, we said that we start with a state. In t equal to 0, we have one state. And then the electromagnetic field is making modification to go into any other state. So with all those definitions and explanation how we do this, and I hope you are interested enough in this topic that you can go to books of quantum mechanics or quantum optics or quantum electronics, that's there everywhere. Okay, so you see, for this coefficient to exist, this must exist and this must exist and be non-zero. And that's why we're going to do now. We're going to analyze when is this is not zero and when is this not zero. Okay? And you have to remember that omega BA now is just the energy spacing between the two states that the radiation is connecting. This is state A, this is state B. This has energy EB, this has energy EA, and the spacing between them, expressing frequency, is this guy, right? And omega, of course, is the radiation frequency. It has to have one, right? Okay, very good. Let's keep this in mind, and let's now see when that's not zero. I will start with that first element that I told you is essential. The first element we have, which is the integral of B, all the interaction, and A. This integral has a sandwich, and this is called the matrix element for the connection between the state A and B. If this is not zero, we're going to call this integral MBA. That integral, the value of this, will tell us how strong is the coupling that the radiation causes between the state A and the state B. So the physical meaning of this matrix element, the way we said, is that interaction acting on A, interaction acting on the state A, original state, may modify it, right? And make it looks like the state B. And that's the only way of this not being zero. If this state A, under the action of the electromagnetic field, changes a little bit, looking a little bit with B, then this integral is no zero anymore. It can be very tiny, which means a weak coupling, or it can be very big, which means a strong coupling. And this element here, this matrix element, is fundamental for anything we do on the light-atom interaction. It must exist. Otherwise, the thing is transparent to light. If this element does not exist, the matter is transparent to light. That's the fact. So let's leave for the moment this this element just as MBA, a matrix element M that connects the state A with the state B through the interaction introduced by the electromagnetic radiation. Now, the time integral, that's a little simpler than the other one, because this thing here is square, this integral is square, which is the time variation, basically give us the delta function times the time, right? So if I go back to my original expression for C, if I come to this C, substitute this by M, capital M, BA, matrix elements connecting A and B, and this by the delta function times the time, we end by having this. And then I divide this probability by time, and when I divide the probability by time, what I'm actually doing is determining what is the rate of variation of the probability, like the speed of probability variation. We call this rate of transition between state A and B. And if you remember, we substitute by a delta function, and the delta function, therefore, is not zero only if omega is equal to omega BA. This is what we call resonance. And we're going to consider resonance. We're going to consider the state, the electromagnetic radiation, with frequency somehow matching the spacing between the levels that we are considering. So this is one. And then the pi stay there. The time t I divide on the other side in the original equation, and I have all those terms. And then I kept the matrix element of the interaction here. So all the time run away now. I have something that's time independent and provides what we call the rate of transition. How many transitions per unit of time this is able to do, or what is the variation with time of the probability to be in that state, which is equivalent. And remember, A square is somehow connected with the light intensity. So if you remember before, A is the light intensity, which is the number of photons that are there. Then we just call we call this W the rate of transition, right? Rate of transition. And that is proportional to the intensity of the light in the frequency that we chose, but we are considering now because only resonance will be possible. This is not true always, but for this case it is. Because even if this is different, we're going to have a line shape that we're going to find out later. But you know, this matrix, so the rate of making a state, original state, to go to the system, the rate in which the system in one state will go to the other that we chose, depend on the light frequency, be in the right matching the energy between the state. And the reason for this is that h bar omega is the energy that the electromagnet is the photon energy of the electromagnetic field, and this has to match with the energy between the two states, right? If you divide here, this matching means they must be about equal. But if I divide it by h bar, means omega equal to omega BA. Because this is the energy conservation, is the energy matching here. But depends on this matrix element. This matrix element, which is the integral between the two states and the interaction, is what connects everything, is what determines everything that is going to happen. Now, I took a state A, which could be anyone. I never said that that was the state of lower energy. I never said anything like that. It can be any state. It can be an orbital with higher energy, can be an orbital with lower energy, can be anything in the system. It's just an initial state, right? That's just an initial state. It's nothing else. Okay, then many things can happen here, and the mathematical analysis provides us all this information. We can extract all this information from this expression now. Because we can ask, when is the rate of transition or the rate of change of the probability to be in one state different of 0? Which means when my system can evolve from the original state to some final state that I chose. Well, there are many situations that's predicted by this interaction. And I want to show you some of them. Okay? We start with the situation. The first situation is the situation when EB, the final state, has an energy smaller than the original state. The original state is EA, the initial state. And I remove the photon energy from this guy, and I end in the final state. So this is the situation where EB, the final state I want to go, is lower. So this is EB, state B, and A was up somewhere. And of course, what's the electromagnetic field is going to do? It's going to bring the atom from A to B. And then there will be a surplus of energy. Where is this energy going? Going to the field back. It's like adding to the electromagnetic field a photon of energy h bar omega, which is h bar omega AB or BA. And this is what we call stimulated emission. Stimulated emission is when I add to the field a photon. So they start with the system in a higher energy state and comes down. So the system, the electromagnetic field, the system is here, and the electromagnetic energy, this is stable, it's there, doing nothing. But comes the electromagnetic field, shakes this enough for this to come down and end in the state B. And as a result, there is addition of energy in the field, which is called stimulated emission. Stimulated emission, as you may know, is the basic fact related to the laser, right? The existence of laser stimulated process is fundamental for that, and many other things that we're going to discuss some in the applications in the coming few lectures. Now, there is a second situation, which is the opposite. Now we consider the state A with energy below the state B. So it's the opposite. I start with the energy below and I go up. The energy of the state B is the energy of state A plus the photon energy. That's another situation. And what's happening in this case? In this case, energy will disappear from the electromagnetic field. That's what we call absorption. So absorption of light is actually when the energy of the light gets smaller. So we come from a lower state and go to a higher excited state. So in this situation, what we have is the system is here, it's there, and the electromagnetic field comes and take the system from there and put up there. And that's the absorption. We work a lot with absorption in applications, especially in biomedical, because basically what we're doing all the time is sending light. When we look into the microscope, we're doing everything. We send light and we see the light disappearing. Of course, you can use also stimulate process to observe things. But now there is a third process, which is unknown from most of you, or maybe you all know. I mean, this is already very common. Suppose that the electromagnetic field has no photons on it. I have no energy in the electromagnetic field. So I cannot really give it to the atom. But let's imagine that my atom, the initial state is above the final state. But there is no photon in the field. It's very interesting because if you consider right, and if you quantize the field, the way I did by putting in terms of number of photons, but now taking better care of everything, it is possible that due to the vacuum, due to the existence of nothing, because the atom is not isolated from the universe, you have fluctuations on the vacuum, and this is something that's very important and made very people famous, like Feynman, Schwinger, Dyson, many people investigated that these fluctuations give origin to what they call quantum electrodynamics, which means that even in the absence of photons in the field, there is no apparent energy in there, it's possible for this state to emit a photon to the vacuum and comes to a lower state. And that's called spontaneous emission of light. And that's very interesting because if we do the calculation correctly and express the A in terms of number of photons, we predicted that. We predicted that it is possible that the field has no energy and suddenly get a h bar omega of energy. Because in this situation, the system is here and there is no photon, but we can think that there are many fluctuations that are like photons being created and destroyed everywhere in the vacuum, and that provokes the system to come down in this spontaneous emission. And the spontaneous emission is very important because, we use it every day, we use it everywhere. So you see, there are three different effects that can take place in this process. And this last one is not predicted by the final rate I gave to you, but it is present if we do the calculation, considering a little more advanced concepts, which is the quantum electrodynamics. And we end by seeing that the atom in the excited state can come down. Normally it can come down in a rate that's determined by many things, the fluctuations of the vacuum, because it was absence of radiation, and the system can come down. So those are the three effects that normally we use during the interaction of light with matter. Stimulated emission we use in many senses. Absorption every day. Spontaneous emission every day as well. Okay, so that's the basics of fluorescence, is the spontaneous emission. We excite and let the system give us back, and look into what's coming back, we can know what's going on there. And in fact, that's happening all the time. We send light, and light is absorbed by pigments, and pigments send it to us the light, and we observe it, nice frequencies, nice colors, all due to this. Okay, so those are the three main effects that we're going to consider. Now, This is generically what's happened. But now we have to simplify the matrix element MBA, as I told you. Because if MBA does not exist, we do not have atom being excited. And the question is, what's happened here? How are we going to simplify? Well, then I want to recall you that this element, this matrix element, MBA, is basically this integral. And what we're going to do is this spatial variance of the field, it is too big, right? Because if you remember, the K is the opposite. K is basically 2 pi divided by lambda. And lambda is micron, right? If you look in the visible light, this is micron. And then here we have an atom that is angstroms, tiny little bit. So for the atom, the spatial variation of the electromagnetic field is not important at all. And we take an approximation to say that this is not important at all. We take that out. No spatial dependence in the electromagnetic field. This is an approximation. If we do that approximation, we can show that the matrix element, MBA, turns to be a displacement between the two states. This small RBA is a displacement connecting the state A and the state B. If somehow by introducing a displacement in the state A, that became the state B, somehow this is not zero, right? This is not zero. Which means that space B is the space A by a displacement, roughly speaking. And that approximation is like, when you have a charge and you make a displacement, it looks like a dipole. And we call this a dipole approximation. So this is what we call dipole approximation, because everything is a displacement on the charge. And displacement on the charge gives origin to a dipole. And this matrix element, finally, is basically the displacement expected between these two states. And normally we just abbreviate that by this bracket type of notation. Basically what you're saying here is that we are considering interactions where the two states are connected by a displacement. And that's why we are dealing with dipole allowed transitions, right? This is a very important set of transitions that happens in nature. And this is natural, right? You come to the electrical field, you make a force on the charge, you displace the charge. And this displacement modify the orbital, and modify the orbital in a way that the energy that the field is able to add is enough to promote from one distribution of charge to the other. And that's when the transition takes place. Let me put this in a more elegant mathematical expression, saying that this MBA, this matrix element, is in this approximation. We can prove that. Don't worry, it's very trivial to prove. Again, I hope you are curious enough to go look for more details. Those lectures, they give you the fundamentals, the directions to go. And this matrix element, as we say, is just the connection between these two states by a displacement. And that's the dipole approximation. So when some people speak about this state is connected to the other state by a dipole transition, means that one is displaced. It means that they must have this kind of integral. This is what we call matrix element. So one is the other displaced, more or less. Physically, of course, we can have an interpretation. It's easy, the interpretation, if you want to think physically, and I think you all want to think physically. We want to have intuition to what's going to is happening. And physically speaking, the action of the electromagnetic field is responsible for the displacement of the charge, transforming one state into the other. And I took as an example here the S2p transition. So let's consider the S2p transition, which is a strong transition. Anywhere you look, they must have some S2p transition. And in this case, what's happened is that we start with the S state, which is spherical symmetric, isotropic charge distribution, probabilistically speaking. Right? So this is what we have here. And here comes somebody and adds to it an electromagnetic radiation. So we added the electromagnetic field, start to make the displacement of the orbital, s orbital, and suddenly when you realize the displacement was enough, I gave enough energy for the system to be in another orbital that looks like displacement. This is displacement of this. I took from here, displace up and down. That's the p orbital. So physically, what this matrix element is saying is that by displacing the charge distribution of the orbital A, roughly speaking, I reach the configuration of the orbital B, right? And this action is really the cause of the atomic transition. This is what makes life possible, are those transitions. There are many transitions, right? But you can imagine inside the plants, photons coming, transforming orbitals, making possible the reaction, make possible the production of reducing carbon from CO2, adding carbon to the plants so they can grow, adding other things, and liberating oxygen that we can breathe. Everything here is due to this. Everything is due to those ways that electromagnetic field can displace charge in very important ways to produce the atomic transition. So this is what we call the transitions. So, and transitions, electromagnetic transitions, or atomic transitions, sorry, caused by electromagnetic field, are the CERN, are the main point, the focus of the light-matter interaction. And we now have all the tools to determine and to study this. But let me tell you, normally we consider a very complex system. We consider an atomic system which has infinite levels. Most part of the time, as you can see, because the electromagnetic field has a specific energy, I can consider as if, right? Or this energy is a monochromatic electromagnetic field, I can consider as, which means single frequency. In this case, the system are able to connect, the interaction, is able to connect only specific states. And in this case, is not hard to just consider, it's not fully wrong, to consider only the two states, right? And that's what we call the two-level approximation for the light-atom interaction. And this is so important that I will consider a special chapter for the two-level system. Because in most of the applications, we consider those levels, a few levels only. Then learning about the two-level system is very important. Okay, so in the lecture of today, we learn a little more and we complete this picture of the light-matter interaction in a quantum level, right? Considering the atom quantized. And I explained to you the three most important effects that's going to happen, and that's going to take place when the light or the electromagnetic radiation in general comes to the atomic system. There are other types of things that will happen as well. You know, we have elastic scattering, we have inelastic scattering, we have many things that has to be considered for a full understanding of the process. But with the basic principles, the fundamentals that we learn on those set of 2 or 3 lectures now allow us to understand all the other ones, as we're going to do in some of the applications. So thank you very much. See you in the next lecture. Bye-bye.